Thank you very much for introduction. Thank you for having me here. It's a great pleasure. I've only visited once Princeton before, I think. I think it was university 11 years ago. I sort of shouted in memory. And I've had a really good time talking to some of you and some others later today and tomorrow. I even got a very nice gift from the university, so thank you for that, this pointer. And I will talk about dark energy today. My collaborators are two of my graduate students, Eduardo Ruiz and Dan Schaefer, and also Michael Mortensen, who is a postdoc at Berkeley, and Wayne Hu from University of Chicago. And if I could summarize this talk in one sentence, I would say dark energy remains one of the key mysteries of present-day cosmology and physics in general. Things have become hard in dark energy. Constraints have become better. We don't fundamentally understand it any much better. And there are still some good avenues for unprobing and maybe ruling out whole classes of models. So there's still hope, so to speak, a lot of hope, I think. So I will talk about that today. I will give a relatively brief introduction to dark energy, assuming that most people are familiar with it somewhat. We are talking about the picture of the universe where energy density in this mysterious component is about 3/4, matter is 1/4, most of matter is dark matter, about 80% of it, and then the rest is, actually this is baryonic matter, only some of it's visible actually, and some of it's in gas and so on. Dark energy, something's been suspected since the 1980s, that something is off in terms of measuring cosmological parameters, and it really all came together in 1998 when two teams independently announced discovery that universe appears to be expanding faster and faster. This discovery, of course, brought the Nobel Prize in 2011. So the picture is this universe is expanding slower and slower because of the pull of matter. And then at late time, about 5 billion years ago or so, it starts to expand faster and faster. Here's the actual supernova data, not the original data, but not too different from different original data. This is supernova data in redshift. On the y-axis is distance, except it's not the familiar distance. I think I subtracted some fixed model, and then I took a logarithm. So the units, so to speak, are not too familiar, but you can look at the shapes of these curves. So this is for a little bit for public talk more. There's a single example of an open and a flat and a closed universe, negative spatial curvature, positive and zero. And people set out to measure which one of these we live in. Turns out the data, this data binned in redshift, so you can see it by eye and judge it. Doesn't fit any one of those possibilities. Instead, it fits a universe that accelerates now, decelerated in the past. And thankfully, doesn't favor a universe that always accelerates, because that universe wouldn't form much structure. We wouldn't have many galaxies. And these classic constraint plots, I think most people have seen. You have omega matter. This is the amount of matter relative to critical, and same for dark energy, actually. So 30% matter relative to critical. About 80% of here, assuming it's a cosmological constant, omega lambda. You see original plots from constraints from supernovae. This is a bit better than original. This is still a few years ago. Cosmic microwave background mainly tells you about flatness, which side on this flat, open, closed curve you are. And then the method called BAO that mostly has to do with galaxy clustering mainly tells you about the amount of matter in the universe. And they all very nicely meet at this model I discussed. And if you relax the requirement that this be a cosmological constant, if you allow equation of state of dark energy to vary as a free constant parameter, these constraints of W have shrunk over the years, shrunk around the value of -1. -1 is, of course, a special value because it corresponds to vacuum energy in the universe. So these are classic constraint plots that I think most people here have seen. So we have very, very strong evidence for dark energy today, that there is something dark, like dark energy. Does anyone want to take a guess at how many sigma do we have evidence for dark energy? So presumably at least 5 sigma, because it won the Nobel Prize. So, but does anyone have a 10 sigma?
What do I get to relax?
You can relax curvature and W if you like. Certainly W. It doesn't matter too much what you relax. If you start relaxing, then things I don't guarantee it. But for the most, maybe more than 10 sigma. More than 60 sigma. Very, very strong. This is just supernova and CMB and BAO. Sorry, I combined supernovae with CMB and BAO, so not just the supernova. And it turns out at this level, it doesn't even matter. This number doesn't change too much if you relax some of the most basic things like W. incredibly strong evidence, more than 60 sigma. I was actually really surprised when I saw this number. I also thought maybe it's 10. So for sure something's going on. The universe appears to be accelerating, whether it's accelerating due to some new component, whether it's modified gravity, whether it's something else we don't know, but it's for sure not some systematic, astrophysical systematic. It would be hard to imagine how it plagues all of these probes. Some obvious systematic anyway. So now, from time to time, so W minus 1, that's a cosmological constant value, is being really good. From time to time, you do see papers saying, oh, some evidence that W is less than minus 1. This sometimes is called phantom dark energy, nothing particular to that name. But let's, we've been hearing about this, so we set out to explore a little bit, is W really less than minus 1 according to some data sets, to at least clarify it ourselves. And let's take a look at this panel here. This shows Planck and BAO and supernova. So this is supernova data I showed. This is CMB. You can think of this as galaxy clustering, basically. This is likelihood. This is minus 1. Planck and BAO themselves, here's the wide curve. And then it's really, once you add some of these supernova data sets that you move significantly, that is to say more than 2 sigma. That's a threshold for getting a little bit excited in cosmology, more than 2 sigma. Away from minus 1, it's these Penn stars and SNLS, supernova legacy survey sets, more so than Union. Turns out Union, the one that doesn't show that evidence, the green line, is probably the most trustworthy one. It's the oldest data set, so to speak. Legacy survey recently, since we did this work, recalibrated their supernovae, and that, I believe, shifted to the right a little bit. And Penn stars is still admittedly in the early days. So,
I'm sorry, so these are accumulating all those different surveys?
Not accumulating, one at a time. One at a time, sorry. Yes, one at a time, either this or this or this. They overlap somewhat. They are not fully independent. So when for example, they all share low Z supernovae. So they're not completely exclusive, but that's been standard for a long time. And so really no, but it's at least to us it was useful is Planck more than WMAP. It's these two data sets more than Union. And then it's more than 2 sigma, but less than 3 sigma. So anyway, we'll see how this plays out. So far, there's no evidence, I would say. However, one interesting game we've played, and this also has been basically known, but we wanted to clarify the picture, at least for our own sake. People measure Hubble Constant, H0, independently. Sorry, 71. This is all in kilometers per second per megaparsec, the rate of expansion of the universe. You measure it from the nearby universe, and that's like independent parameter you can measure. So what happens when you add Planck and BAO and some supernovae together with the measurement of a Hubble constant? People disagree on this. This used to be 50 or 100. Now it's converged about 70 kilometers per second per megaparsec, but some people say it's 68. Some people say it's 72. So assuming H0 is this value on the x-axis, plus minus, I think, 2.5 or so. So plus minus the standard, more or less, error bar that people quote. What are the constraints on W? Again, you're looking for departure from W equal to minus 1. And you can see that if you were to claim, as some people did, the Hubble constant greater than 71, 72, certainly in the mid-70s range, if that were to persist to be the case, then that would pull away from W of minus 1. If Hubble constant ends up being somewhere in the 70 or less, then W is, again, good to be. The background to all this is discovering for sure that W is different from minus 1 would be truly a tremendous discovery. It would rule out cosmological constant. Mother Nature hasn't cooperated so far in that direction. And everything is consistent with W minus 1. But here's how things would change. It turns out, perhaps surprisingly, though not so much for the experts, this astronomical parameter, Hubble constant, actually has a lot of say on the constraints on dark energy.
The error bars are 1 sigma and 2 sigma?
1 and 2 sigma, correct. Marginalized over all other parameters. Pretty much full-blown analysis. Yes, Tim? They certainly do. They do. That's where things get complicated. I'm not so familiar with Penn stars. I'm more familiar with some of the others. Main systematic have to do, there are some nuisance parameters. In addition to the original broader is brighter nuisance parameter, they now fit for correlation with color of supernovae. It gets a little bit more complicated after that. The answer is yes. So stepping back for the moment from the W analysis, we have a couple of big questions. These are big questions in the dark energy world. Is dark energy something other than vacuum energy? Does GR self-consistently describe cosmic acceleration? These are the questions that many, many people are working on. and that many thousands of papers have been written on. So this is sort of the big motivation. And in the remainder of the talk, I will briefly talk about a couple of topics. One of them is testing dark energy with geometry and growth, which I think is a very promising avenue. It's not a new idea. I think it's a really, really good thing that's going to keep us occupied for the next, say, 10 years. And then making predictions for dark energy observables, which is very much similar tone as this first topic. So this work, before I go there, I mentioned distances. Let me remind you of the most important thing to know about dark energy and the growth of density fluctuations. Dark energy simply suppresses the growth of structure. It pushes things apart at late times. It suppresses the growth of structure. So here's a very simple couple of simulations. One is with dark energy, one is without. They're made so that this is in the past, this is today. They're made so that today they form about the same amount of structure. So I know these look visually a bit different, but let's just assume this is the same amount of structure today. And then it turns out if you have dark energy, it suppressed things. You had to start with more structure in order to get there today. If you don't have dark energy, you get a lot of growth, so you don't start out with a lot of structure. People often normalize today because today is when you measure things the best. So
I always find this to be misleading because we know the microwave background better than today.
yes.
So the people often say there's less structure in these models, and when you normalize the
That's right.
CMB, you get the opposite state.
That's a good, very good point. Yes, I agree. You can, for the purposes of illustration, you can look at it one way or the other. Yes, but yeah, very good.
But all the stuff you do when you combine data sets, you almost always include CMB.
That's
So if you want to understand what the predictions for numbers of clusters are, for example, it goes opposite of this.
That's a very good point. I fully agree. I was in possession of this set of slides from before, so that's all I can say. I fully agree with you. That's exactly right. That's sort of the basic starting point, is to normalize. Regardless of that issue, dark energy suppresses the growth of fluctuation. That's the most important thing to know. So our idea, this is PhD thesis work of my student Eduardo Ruiz, which will be on archive in about a week or so, is to compare geometry and growth. So this is not a new idea. This has been on for a long, long time, probably before these, but here's a Princeton paper on that. And our close cousin is particularly this Wang et al. Paper, which did a kind of a similar thing we did, except we did it in a lot more detail, I think, and with better data. So here's the idea. So the general idea is, why compare geometry and growth? Because if you have any model, say lambda CDM, geometry and growth are not independent. One predicts the other. In other words, if you have some geometry, then you have some growth, right? You can't independently change the two. Some geometry and some growth history. So here the idea is, very specifically, double the number of parameters that describe dark energy. Canonically, it's almost always one or two parameters, assuming a flat universe, which we do for the most part. Omega matter is one parameter, and equation of state the other. That's the parameters I talked about. Now you have omega matter and W for geometry, and you have omega matter and W for growth. So whenever you measure geometry, you measure these. Whenever you measure growth, you measure those. So you have to separate in your cosmological probe, which one am I measuring? It's always one or the other. And it can be both in a single probe. So we've done analysis, marginalized over all the other parameters. I think basically try to do everything correctly, nuisance parameters depending on the probes. I was not planning to talk about data we use a lot. I will breeze through it in one slide. I can say a couple of more words about data set if people are interested. We use a whole variety of cosmological data, and this slide to me is just impressive of what kind of data we have today. It's really incredible variety of powerful data sets. Supernovae are the most familiar. I've talked about supernovae already, ballpark 500 supernova. They're distance measurements, basically, for physicists. Clusters, you can count the number of biggest things in the universe, biggest objects, galaxy clusters. This is Max BCG catalog. Masses have been determined using weak lensing. There's about 10,000 clusters, I believe. So you count clusters. Redshift-based distortions is a feature in the clustering of galaxies because you observe the clustering in redshift space, not in real space. It's a little bit technical to describe in a maybe popular language, but it's a powerful probe of the growth mainly. Cosmic microwave background is, of course, famous. And the interesting thing about the CMB is that it provides incredible variety of constraints on the early universe. For dark energy, to the lowest approximation, it gives you one number, which is a distance to the last scattering with certain conditions imposed on it. So very accurate one number, very important one number that helps on dark energy. Weak gravitational lensing, this is new, I think, probably to most people here, even to me, this was new. Weak lensing's been around for a while, measuring slight distortions of shapes of galaxies and learning about the structure between us and the source galaxies. So far, constraints from weak lensing have been not only weak, but really only hard to use. So this survey CFHT lens at the Canada, France, Hawaii telescope did a really heroic piece of work. They, in addition to publishing very nice papers, they made available theorist-friendly data constraints, power spectrum. So that's very, very nice. You can go download it, beautiful data in 6 redshift bins. So error bars are very big, but there's a full covariance matrix, all the data points. So it's really, really nice. This is mostly novelty where this has gotten recently, because it's subject to a lot of systematic errors. And baryon acoustic oscillations are familiar from Sloan and extension. And anyway, we use standard measurements of angular diameter distance due to the BAO. So I realize I'm not maybe talking in detail about these, but we use, this is really quite an extensive current data, all of it more or less trustworthy, you know, really professionally obtained.
On your redshift space distortion curve, that lambda CDM curve, you must use the amplitude from CMB.
That's right. So this is a funny space, which people, I haven't seen this plot in this space before, but the parameter, usually you see F sigma 8 versus redshift. Here, F sigma 8 on the x-axis, it's the amplitude that people, that mainly these constraints, and there's actually F of z, I'm gonna mention it in the next slide. It's this Alcock-Paczynski parameter that combines Hubble parameter and distance. So mostly, this is a lambda CDM, just vanilla theoretical curve from Planck. There's no fitting here yet. Or a Planck amplitude, yeah.
So I mean, I think there's really, I think there are 2 numbers you get from the CMB. The peak position, you know, the angular diameter distance, and the amplitude.
Oh, I see. Yeah, that's what you're getting at. Yes, yes, I guess that's a good point, because I usually think of it as just the distance, constrained omega. But now that we want, sorry, so maybe I rephrased my story a little bit, because you're right. One number for the sort of geometrical things, but now that we're talking about growth, that's right. So there's amplitude, you are comparing to theory, so there's amplitude from the CMB. I believe that's right. Now it's very interesting to sort out what probes what. So here's cosmological probe, who does geometry, who does growth. Supernovae obviously do geometry. This is the one thing that maybe most people here are familiar. They measure distance, more or less. There are some nuisance parameters, but for physicists, this is the distance measurement with h0 times distance, which is very nice. It doesn't even depend on h0, because distance starts out as 1 over h0. Baryon acoustic oscillations, again, to an approximation that's good enough for current data, measures 2 directions in the sky, give you angular diameter distances, and 1 radial direction in space gives you h. So the combination measured is this parameter, sometimes called dV, which is combination of distance and h, and that's a geometrical. You can also do the separate, but I haven't done this analysis myself, but to the best of my understanding, this is good enough for the current, which might be arguable, but anyway, this is what, that's right. The CMB peak location is, so turns out CMB, you can of course do the full analysis, but it's a really good approximation if you, assume that angular diameter distance, you extract that from the CMB, it's a meta parameter. It's something that's constrained halfway to the reader. It's published in papers, and it turns out it's with omega meter h squared fixed. So if you multiply this by square root of omega meter h squared, it turns out this has a little bit different properties than your standard angular diameter distance. This whole thing is known as a shift parameter to aficionados, and that's what the CMB. I will also have a CMB early universe prior later on, which is not in this table, where David's comment about amplitude comes in. That comes later, but this is sort of at the level of before what we call the early universe prior. We are really concentrating on the late universe here, so to speak. Cluster counts, number of clusters is equal to volume times the number density. Volume is geometry, number density is growth. Weak lensing, you are observing these shapes. The equation is more complicated, but you have a geometrical factor for gravitational lensing. So gravitational lensing has some distances, has Hubble parameter. W is just the lensing efficiency. It has to do with your lensing sources are. So that's probed. And then for growth, it's the power spectrum, the 2-point correlation function of matter. So this is your just standard matter. And then for redshift-based distortions, mostly it's this F sigma 8. So F is the rate of growth, and sigma 8 is the amplitude of mass fluctuations. So you can think this whole thing is very, very much growth of structure. It's mildly sensitive to a geometrical parameter called f of z. So here's the standard constraints. So this is before doing anything particularly new. This is the omega matter sigma 8 plane. And in this plane, we should be recovering constraints that other people are getting. Omega matter, sigma 8, supernovae, not getting much help. So that's why they look wide in this plane, because we are not giving them help. Most of the other probes, we have to give some help. Help comes from the early universe. That's the Planck prior on these 4 parameters: physical matter and baryon densities, spectral index from inflation of scalar perturbations, and the amplitude of fluctuations. So you can think about this as early universe. We want to concentrate on the late universe. So this 4x4 covariance matrix, sometimes, anyway, there's analysis details here. That's often provided as a prior, one at a time, just to make these contours be finite. Otherwise, they blow up because there's a number of cosmological parameters and not enough measurements. Sound horizon is a subset of those constraints. What I like about this already is so there's some standard suspects: CMB, baryon acoustic oscillation, supernovae, redshift space distortion, clusters, and combined. Weak lensing, most often in papers, you see combined with a lot of other things. So this is a little bit more minimalistic, trying to answer what exactly weak lensing covers. And it can't do much by itself, but with a little bit of help, it gives some contour. Constraints omega matter of 0.3. And this parameter, which when I was in graduate school not too long ago, was between 0.6 and 1, has now quite nicely converged already for some time around 0.8. And then omega matter and W, again, what you're looking is W minus 1. Yes, it is. And you can look at these constraints and draw some conclusions. But anyway, this is all more or less. Other people have done this in many papers. Yes?
Kind of looks to my eye like on that left plot, those contours overlap less than I would expect if they were just independent statistical calculations.
Chi-squared is, the goodness of fit is good. So I can say that. It's, yeah, that's right. That's, I would honestly be surprised if that weren't happening, if everything were just lying on top of each other. You're right, the goodness of fit statistic is good, but I have a bigger surprise coming up just now. So it's not a surprise, but so surprise is not just yet. This is now a first of these results where omega matter is split into geometry and growth. So this is omega matter. Anytime you see geometry, you're measuring this omega matter. Anytime you're measuring growth, you're measuring that. You expect to be somewhere on the 45-degree line, right? That's your expectation from the model. If you're off, and if you're sure of that, then you've ruled out a lot of things. And things do lie on the 45-degree line. You can study these. Of course, supernovae and CMB and BAO have to be only geometry. RSD is mainly growth. The one new thing to me in this graph was clusters, which is yellow, just how much more they are sensitive to growth than to geometry. So this, I always thought it's one and the other, but it's really a lot more growth than geometry, which maybe some people knew, but I didn't. Now we come to a bigger surprise and the most challenging plane to constrain. Here's why. We split W, geometry and W growth, in addition to all the parameters, as well as nuisance and cosmological. There's also omega matter growth and omega matter geometry to marginalize over. So this is a very, very difficult plane to constrain. It has at least 2 more parameters than what you're used to seeing. And this is why some contours like weak lensing are all over the place. Most of them individually, even with the early universe priors, are all over the place. Some of them still hold up. They are so specialized, they do well in this space. But the big surprise is the combined contour is 3.3 sigma away from the 45-degree line. Now, that contour is dominated, though this is not only due, dominated by redshift space distortions. So redshift space distortions, this has been known in the literature. They tend to prefer less growth recently. And if you think about it for half a minute, that means W greater than -1, more suppression. The closer W is to 0, the more suppression. You can think about it in the extreme case. If W of dark energy were 0, dark energy would scale like matter. But it would be like matter that doesn't cluster. that would be a disaster for formation of galaxies. It would be 75% at all times and not clustering, so there would be not a single galaxy. So that's how you think about going with W above that suppressive structure.
So that's just using the register space data without using the prior from the CMB for amplitude.
It has an early universe prior. So
What is constraining you on the x-axis? It's hard to read all those mini contours. The fact that that you're getting W, the best fit W geom is slightly negative. What of all that is?
yeah, to that question, I'm not sure I know the answer offhand. There's things pushing you, and again, of course, what happens here is ellipses. Degeneracy is breaking in the full n-dimensional space, not in this two-dimensional space. So it's a bit hard to watch here. I haven't dug up the answer to that, but that's a good question.
It looks like BAO.
Yeah, you just combine BAO and Richard Spencer social.
But that's right. But if you just do RSD, you can actually get good constraint on W. That good constraint is quite far from -1. So you don't even have to be talking about the x-axis. You can just ask what's the constraint here.
There's two funny things. One is that you're away from -1. The other is that the two W's disagree with each other.
Uh-huh.
And you're making both statements, right?
That's right. So you're saying if this moved to the right, then I guess, well, you would alleviate both if you well, yeah. Yeah, I don't know at that level, breaking up those two. I mean, certainly, you could move back to the line this direction or this direction, but it's really, you're right about that.
So at the Solvay meeting, Stocky said that he thought the value of tau would come down because of the 343 gigahertz correction to the WMAP. WMAP for Planck. To WMAP, because 343 gigahertz to WMAP for correcting Planck. And also one thinks that omega matter might come down from the Planck 2013 paper, which seems plausible.
So after I heard you say that over lunch yesterday, I was doing calculation while I was taking a shower this morning, of all things. And if tau goes down, because tau and amplitude of mass fluctuations that combination is constrained very well. Tau goes down, amplitude will come down, RSD will be alleviated. But if I did this in my head correctly, not nearly enough for the change of W that you were mentioning.
Right, I think you want sigma 8 of about 0.8 above, which is where things basically, I think with that value, everything sort of fits.
0.080.
Sigma 8.
Oh, sigma 8, okay. Yeah, I think, yeah, that's very interesting. What happens to that? I don't think, from thinking about this morning, that'll be sufficient. So let's look at this in a little bit more detail. So that's where. So first of all, recall our data. This is our F sigma 8. So remember, this is what theory curve was. Ignore the dashed contour for the moment. Most of the RSD data like to be to the left of this. Now, we've tried one thing. So we had some choice for the data set. Of course, now you can start picking and choosing this or that. That's completely a posteriori. But one thing is clear. Even within BOSS, there's multiple analyses of the same data. So this is the so-called Chuang et al. Paper. And we decided, what if we replace this most discrepant data point with a Samushia et al. Data point? So this is Chuang et al., Samushia et al., both BOSS. They disagree. The BOSS people don't really know why they disagree offhand. There could be different reasons. It's not really known. So what if we replace this data point with this data point? But not start replacing everything, because then doing that, of course. And then you get the change in the left panel. So you go from this combined constraint to the darker combined constraint. You go to 3.1 sigma from 3.3 sigma. Similar thing. What if you get rid of RSD altogether? Then you alleviate, but not by a huge amount. And I think Michael's question actually now, I think, is quite pertinent here. This is still at -1.2 and not at minus. But anyway, even if it's not just the RSD.
Could you go back to the plot? No, sorry, the one before that.
So you just got rid of RSD.
Yeah, I'm just confused. If you take away the RSD,
Yeah, you can look at this plane and say how things, because things are in 10-dimensional space. So you're breaking the degeneracy in 10-dimensional space. So it's very hard to look at two contours and tell how they're going to combine in this space, right?
yes, but you're also breaking them in the 10-dimensional space in the plot that comes ahead. So, I mean, I understand that
Right.
you might not necessarily see all these things combined, but if I look at the plot that you just showed, where you take away the Richard Spencer distortions, I still think it's a little bit.
Yeah, I really can't trust my eye looking at this, because remember, the two omegas, geometry and growth, very degenerate parameter with these are marginalized over. So I would at least want to look in the 4D plane, which I can't, of the two W's and two omegas to draw conclusions about. So I really don't trust myself, at least. But yeah, so we've done some tests. Obviously, these are not any ultimate tests. There's one more obvious way to go, which others have done already. Beutler et al. Boss paper recently, not too long ago this year, claimed that non-zero neutrino mass. So what if we relax 0.06 eV to varying neutrino mass? You relax things.
Wide open, or do you put on some prior?
0 to 1, but it doesn't matter, EV. It doesn't matter because the constraint is much better than 0 to 1. So it's wide open. But the data wants it to be here. And if you fix, I want to be on the 45-degree line here in the 2 omegas, so you get the same thing but narrower. So it's about 0.45 EV. That's completely consistent with Beutler et al. Boss paper, which says if you have 0.3, 0.4 EV neutrino mass, this gets relaxed. Of course, who knows? It could be some systematics in one or more data sets. But it is just a fact that neutrino mass can help. But I think claiming that neutrinos have mass just from this would be quite a reach. Some of the neutrino masses. Some of the neutrino masses, I apologize. Some of the neutrino masses, constraints tends to suppress the structure growth. So that's what cosmology is sensitive to. Yeah, I should give some background to that. Thank you. Cosmological data so far have an upper limit, mostly Lyman alpha, anyway, some data, which varies depending on who you ask. Upper limit on the sum of the masses is anywhere between 0.3 and 0.5-ish EV. Now, if this were true somehow, it would be favoring at the very high end of that upper limit. So it's not completely inconsistent. It's a very interesting story, I think. I think it'd be a reach to claim neutrino mass non-zero. It'd be a big discovery, much bigger than the hierarchies, one hierarchy or the other, which is 0.10 EV, I think. But it is an interesting direction in which things may go. But anyway, so far the upper limits from another probe are something between 0.3 and 0.5-ish. Any other questions about this? So it's interesting. This has been noted before. But what I really like about this is I like these particular parameters as a very good scan into what is exactly going on, as opposed to some other parameters which don't really tell you what's going on in terms of growth. And for the second topic, in just 10 minutes or so, I'd like to talk about making predictions. So now for something a little bit different on the same general topic. This is a little bit older work with Michael Mortensen and Wayne Hu, to make predictions for dark energy observables. So the philosophy is this. For any given class of dark energy models, say, for example, lambda CDM, there are only two parameters, omega matter and the Hubble constant. W is -1. Universe is flat, so dark energy is 1 minus omega matter. And so if you measure those two and you do so well, then you can predict distance, growth, Hubble parameter at any redshift, right? Because you know that your Hubble constant is 70 plus minus 2, and you know that omega matter is point something plus minus point something. So you can calculate these functions and predict what you should be measuring at any other redshift, even for probes you haven't used so far. So these are therefore target quantities that you can target with future data. So this is I think, very nice way to think about how to use future data to probe things. So maybe to make this clear, let me mention methodology is slightly more technical language, but maybe, at least for some, this will make it clear. Say you have some parameters. For omega lambda is just, so for lambda CDM is just matter and Hubble constant. You may allow universe to be non-flat. You may allow not just W, but W of Z, so free function in redshift. So that's many parameters. This stands for early dark energy. That's dark energy that's important at high redshift. Don't worry about that, but we allow that as well. Use some data, current or future, likelihood machine. You constrain these parameters. From those parameters, you compute these functions, right? So you can, for example, you can predict distance at redshift of 100 or redshift of 10, anywhere. You can predict Hubble parameter where you never measured it before, just because you constrain parameters. It's a very simple idea. So I'm going to show several plots now. They will all look like this. On the y-axis, I will have the relative theoretical, so to speak, fluctuation, uncertainty, range in some parameter O. As a function of redshift, don't worry about this. As a function of redshift, there's going to be two ranges of models. There's going to be more constrained model A, for example, flat lambda CDM, and a more complicated model B, for example, curved lambda CDM. And then there's going to be one curve that tells you just how a generic model looks in this model B, right? So this is a model where O, delta over O around the fiducial varies like this.
I'm sorry, we're looking at, are the contours showing observational constraints or theoretical range of theoretical predictions?
Both, sort of. So I can calculate distance given some omega matter, and now I have a range in omega matter and this and the covariance. So I use that within that range, distance will vary. That's what they show, around the mean or fiducial.
So there's no data or assumed data in the plots yet?
I haven't shown any, but the data will be assumed. So for example, current data, this is in 2010, I think, or 2009. Current was this, and future will be something. So future, so imagine you use some current data, again, to get constraints. This is 0.3 plus minus something. This is 70 plus minus something. And then I plot the range of distances I get. But I subtract the mean so I can look at it better. Does that make sense to? So here's the kind of thing you get. And again, I said you can plot anything. So growth, both to redshift of 1,000 and to redshift of the 0. Don't worry about the difference. You can plot growth relative to the mean. This is for current data from 2010. You can plot the distance. You can even plot more exotic quantities. This is sort of like F sigma 8 I talked about. This is what redshift space distortions measure. Hubble parameter, even what's called the growth index. So don't worry about all of these. So what do we have here? The gray region is flat lambda CDM. There are only two parameters, omega matter and H naught. So it's not surprising that distance and growth are very well predicted to about a percent or two away from the best fit values. And if I allow curvature to float, now I have omega curvature, the third parameter. So now I have more freedom in my functions. Because I have more freedom in my functions, these are 1 and 2 sigma contours, the solid and open, I go wider. So here's the idea. Let's say tomorrow somebody has a great experiment that measures Hubble parameter at redshift of 2, which we haven't done. If you have an error bar that lies here outside, if the measurement error were small, if you're sure of everything else, then in principle, you've ruled out flat lambda CDM and curved lambda CDM. So this is a little bit of a cartoon. If I lie here, overlap with blue, not with statistically, this wouldn't be significant, okay? But if I lie here, I've ruled out the gray model, which is flat lambda CDM, but I'm consistent with curved lambda CDM. And of course, if I lie somewhere across this, then I'm consistent with both. So you can't confirm models, but you can rule out models, right? That's the idea. So that's a general idea. And the main punchline here is all quantities to better than 5% at all redshift of interest. If now you might think, okay, if I allow W to vary, especially W of Z in principal components, we assume 15 principal components. So this is 15 more parameters, 2 or 3 parameters plus 15 more, describing this function W of Z that can be between -1 and 1. This is a function now, W of Z. You might think it all breaks down and you fill up the whole plane. So that's far from true. It turns out all of these quantities, you can see typical model now can fluctuate a lot, right? You can especially see that in the Hubble parameter. All of the quantities still to within 10% or so. And then you can look at the specific deviations and you can understand them all, which I won't do here. For the future data, same thing. So this is future, just assuming some future data, assuming you have some constraint around some. So here, fluctuation is around some fiducial model you assumed ahead of time. But the important thing is the error bar. And again, flat or curved lambda, good constraints. And you can even find some sweet spots that are really good if you're designing your experiment. And if you have enough freedom, if you truly have freedom for some more choice, especially of redshift or probe, then you might want to target these. For example, Hubble parameter at Z of 1 in flat lambda CDM is predicted to 0.1%. The reason is pretty simple. There are only 2 parameters. So you get kind of pivoting kind of behavior in H of Z. And you know, that's basically why you get sort of this neck. So this might be particularly nice. You know, ruling out the gray model, of course, would be a huge deal. Ruling out lambda CDM. So targeting this is not completely unreasonable given freedom, which we usually don't have in building experiments. Finally, you get the idea what's going on here. If you have quintessence, some future data, it doesn't matter. You can look at these smoking gun signatures going, for example, from flat to curved, and you can understand them. For example, curvature increases distance to recombination, so dark energy is allowed to decrease it, to go down. This is the blue region in the curved case, at low redshift to compensate. So, you know, if you end up here, you may have ruled out quintessence even, scalar field with the free equation of state in the curved space, sorry, in flat, but you are consistent with curved. Therefore, whole classes of dark energy models are definitely highly falsifiable. What I didn't quite say, and what I think some of you are probably thinking, is how easy or hard is it to put new error bars in those graphs? It may be hard. Some quantities are more difficult to measure than others. But for sure, the ranges predicted in these generic quantities we measure in cosmology are a few percent, even for relatively general models. So I think this is a reason to be optimistic in a field where things have become quite hard, quite honestly. Right? And people have pushed this even further. So Wayne Hu and his group, Van der Velde, Mortensen, Hu, and Eifler, they wrote a follow-up paper, because these quantities I had before were real theorist quantities, growth of z and distance of z. But let's go a little bit toward observations. You can predict what kind of shear two-point correlation, what kind of weak lensing power spectrum would you predict, given constraints from, say, current data at the time. So this is psi plus, so zeta plus, this is this two-point correlation function as a function of theta. Now, it depends on the depth of your survey. This is a shallower survey. This is a deeper, or vice versa. You know, one is shallower, one is deeper. And then there are actual error bars that mostly agree. So I think the pink error bars, purple agree with, should correspond to blue, and black correspond to gray. But you don't just have to predict growth and distance. You can predict observer's quantity, so to speak. Angular two-point function, in principle, flux, and angles from the sky, things that astronomers measure. You can, in principle, predict those. So I think that's quite nice. It's quite predictive. I think I'm approaching the end here. I know people at Princeton are doing a lot of things, including PFS, including spectroscopic surveys, and one I'm quite excited about is Desi. I think, though I'm not 1,000,000% sure, Princeton is not on this one, so I'd like to just mention a couple of words. It's a big spectroscopic survey at Mayal telescope in Arizona, 5,000 fibers, covering 15,000 square degrees, 20 million spectra, over 50 cubic gigaparsecs. How you count cubic gigaparsecs is a bit iffy, depending on how deep you go. But to me, I think of this, a theorist, 20 million spectra, 50 cubic gigaparsecs, huge volume, 3 different kinds of probes, luminous red galaxies, emission line galaxies, quasars. In my mind, 2 things. Of course, many more than 2 things. Dark energy and primordial non-Gaussianity. Primordial non-Gaussianity, big volume, really, really helps. So some of these fundamental things, dark matter, dark energy, primordial non-Gaussianity, funding DOE plus institutions. We at Michigan bought in recently. We put in $1 million, bought into this. And our experimentalists from Michigan got a contract to build fiber positioners. I'm saying this like I know what I'm talking about, really, but it's an important part of the focal plane. And of the, so it's pretty exciting. And that's happening whenever a year is given, always at plus minus, maybe plus, potentially a year or 2, I don't know, but that's roughly the date. It passed the CD1 phase of DOE reviews very recently. That's Desi, international collaboration, many institutions, dozens of institutions. The P5 ranking, which for those not completely familiar is a particle physics prioritization panel, very influential panel that ranks things in particle astrophysics and, of course, particle physics. Ranked, for example, LSST got highest ranking in all. So there's a good scenario, worst scenario, really bad scenario, I think, roughly. And Desi was recommended for good and medium and dropped out in the really bad scenario, was under. So that's roughly what happened at P5. We are hoping we are not in a really, really bad scenario, but we'll see, we'll see. So. So in conclusion, so far, measurements are in excellent agreement with lambda, despite occasional alarms to the contrary. I talked about this one possible alarm. No reason to think W is not -1, though this may change depending on Hubble constant. I talked about the great benefits separating geometry and growth, getting not just constraints, but insights into what data are telling you. And I talked about RSD in particular being a misfit for the moment from the lambda model, which we'll see what happens, and maybe it's due to systematics. We also have these excellent tight predictions for cosmological quantities, and I think it's a way to certainly get more enthusiasm and to have some nice predictions. And if we are lucky, Mother Nature cooperates, and we are able to rule out, certainly lambda CDM comes to mind, a class of dark energy models. So far, it hasn't done that, but if it happens, I think it would be very helpful to the field and to us.